Hey everyone, this is Daniel for Rock the JVM, and this video is about performance optimization in Kafka producers and especially consumers. Now, for this video, you will need to know some Kafka foundations and perhaps some Kotlin basics because the code examples that I'm going to demonstrate in this video are all written in Kotlin, although we aren't using any rocket science and the code examples can easily be translated to Java or Scala. Now, to make the most out of this video, I recommend that you follow the code, which means you need to clone a GitHub repository and run the examples with me and follow them as I demonstrate what's happening under the hood. This video is a little bit different than the rest of the ones on the Rock the JVM channel, or most of the ones on the Rock the JVM channel, in the sense that usually I write code from scratch and demonstrate what's happening, but this code example is a little bit bigger, so rather I'm going to walk you through what's already there, and you can use the GitHub repository as kind of like a template or a starting point for your own experiments if you're a heavy Kafka user. And obviously, whenever you need to refresh your memory, just refer back to the video or to the written form at the blog with the link in the description. My old Rock the JVM student, now streaming expert and solutions architect, Giannis Polizos, wrote a long-form blog post describing everything that you are also going to see in this video. So to make the most out of this video, I recommend that you have the blog post handy, so you can click on the link in the description and access the blog post, and you can find Giannis's explanations here in written form if I'm skipping anything. The second thing that I'm going to ask you to do is go to the GitHub repository that he set up for this blog post. So I'm going to have a link to that in the description as well. You need to clone this repository and run it locally. You'll also need a Docker Compose to spin up the Kafka cluster, which Giannis already set up in this Docker Compose YML. I'm also going to walk you through what the code repository does. And to test with the actual data, we have a Kaggle dataset. I'm also going to link that in the description. A Kaggle dataset with e-commerce data. And the data is quite extensive. There's multiple dozens of gigs of data. We don't need that much data, but you need to download one file and scale it down to maybe 100,000 or a million or a couple million events. So you can pause the video to download or set up the repositories if you need. And after we've done that, I want to walk you through the repository. This is a Gradle repository, which you can import in an IDE such as IntelliJ IDEA. This is kind of the go-to option for Kotlin. So this is where we are going to spend the rest of our time in this video. And obviously in the source folder, I'm going to walk you through the kinds of stuff that we can run and tune. So we have application YML, we have logback XML. These are all pre-configured for you. You don't really need to do any of that. So I'm going to spin up a terminal where I'm going to start the Kafka cluster. And the Kafka cluster here is specified in Docker Compose YML. This has already been set up for you. So I'm just going to run the command docker compose up so that we can spin up the Kafka cluster. So we're going to send a 3-node Kafka cluster with a zookeeper in between them. So as this is spinning up, we can load a bunch of data and we can run the applications, plural, as we go through this repository. Now, I'm assuming that you already know the foundations of Kafka, so I'm going to get straight to the point. This is the kind of general architecture of a producer-consumer simple scenario where Kafka sits in the middle. And right now we're going to focus on producers, which read some data from an external system, and this is, in our case, a bunch of CSV files, and the consumer simply consumes the messages if and when it becomes online, and Kafka has a bunch of brokers, and every broker has access to topics, which is split into partitions and segments and batches and so on and so forth. And at this point of the video, we're going to tune several configurations in Kafka so that the producer is able to send more messages to Kafka at the same time. So here I'm going to go to producers, and here under producers I have an application called event producer. The event producer has a main function, and the main function simply calls e-commerce producer.runProducer. This is a simple object which has a function called runProducer. So this is essentially what the main function does. And you are going to load the events as a sequence, so as a pretty much a stream of click events. This is a custom data structure that we built for this particular scenario. And the click event is just the data structure that is described by the CSV. So the CSV, I've already cut the data down to 100,000 elements so that we can process them. And I did that so that we can process the data in a decent amount of time on camera here in this video. So you can cut the data down to 1,000,000 elements or 5,000,000 elements and notice the time differences and performance increases on the kind of scale that you're comfortable with. So this is a data structure that we've built. And the event producer contains some data source util.load data file. This is just a utility function that loads the file as a CSV. This also does some parsing, and we have this little constructor data source utils.toEvent, which is pretty much a CSV row parser, and this builds the data so that you don't have to. This is why I'm only walking you through the kind of code that we've written here, or that Giannis wrote, so that we don't really have to type in CSV parsers, because that's not necessarily the purpose of the video. All right, so we have the events as an in-memory data structure of all the events that we're going to read from the CSV. And the Kafka config just builds some producer props. This is the kind of properties that we are going to tune for performance. Now, after we create the properties, then we're going to create what we called a producer resource. And the producer resource is essentially a wrapper over a Kafka producer, so a regular Kafka producer that has a bunch of auxiliary methods, so nothing particularly rocket science. It only sends events to the Kafka producer while performing some side effects. So it logs exceptions or errors or counts or time it took for the producer to send a bunch of messages. So this is a plain wrapper over a Kafka producer that only logs some additional data for us to analyze. In particular, the important method is the produce function. So we have a producer record which has the topic that we're going to create, the key and the value. These were made generic with K and V. So these are the type arguments to produce a resource. This is nothing special for us. We have the key and value set in the events themselves. So we're going to create a producer record on these ones, performing a side effect. And on the side effect, we're going to send this producer record to Kafka and logging the exception if it's not null. Otherwise, we're going to increment some counts and logging every 100,000 elements. So this is the kind of code that is going to get run for every element. So if we get back to the producer resource, we are going to say for event and events, we're going to call the produce function on this producer resource that I've just demonstrated. And we have a little function called measure time in millis so that we can count the total time it took to produce this many elements. And we're going to simply log everything out to the console. So nothing particularly rocket science, but this would have taken a long time to type. All right, so with that being said, I'm going to spin up a new terminal while the Kafka cluster is running, and I'm going to do a docker ps, and I'm going to try to find one of the identifiers of one of the nodes here. I'm going to use this one. So I'm just going to say docker exec -it this thing bash, so that we can create a little Kafka topic. And I'm going to navigate to opt bitnami Kafka. This is where the Kafka installation is present on the Docker containers. And then I'm going to create a topic. So I'm going to say bin .bin Kafka topics create, and I'm going to say topic. And the topic name is important because this is referred to in the code. So I'm going to say ecommerce.events, and I'm going to say replication factor 3. So replication factor 3 and partitions. So partitions 5 and the bootstrap server. So bootstrap server. And for the bootstrap server, I need to be careful with the ports. So if I do docker compose YML, I need to look for the internal port in the Docker container. So the internal port is 29092, and this one is the external one that's being exposed on the machine. So I'm going to use localhost 29092. So it's Kafka topics.shell. And okay, we have created topic e-commerce events. Good, great. Now, at this point, we can run our first application, which is this e-commerce producer. And here under the Kafka config build producer props, I'm going to comment out the batch size config, linger millisecond config, and compression type config, because these will improve performance for producers so that you can see the performance difference these configurations make and what these things do. So I'm going to comment these out in build producer props. So the 64020 and gzip. And I'm going to run this application, this event producer Kotlin here. It takes a little while for the repo to warm up the compiler, and then the compilation will only take a couple of seconds, and we will see the logs and the time it took for this data file, the ecom 100K, to be processed. Also make sure that the data file path is relative to your home folder. So I'm having my home folder /dev GitHub, and then I have my little paths here. Okay, so total event record sent. This is 100,000, and total time 3 seconds. This is the total time it took. Now, if you want 1,000,000 elements, and if you want more, you can take out the data file and you can trim it down to 1,000,000 elements instead of 100K if you want to process more elements. So I can create a new little terminal in my little IDE, and I can say head-n 1,000,000, and then I can do tilde desktop. This is where I downloaded the big data file from Kaggle. So I have 2019 October CSV, and I'm going to put that into data, and I'm going to say ecom, and I'm going to say 1,000,000.csv. So this will take 1,000,000 elements and put this into a new file. I had 100K. We can process this 100K or 1,000,000 here in the path. So I can rerun this application. So where is that? I can run the event producer Kotlin, and the time should be 10 times as big. So we had 3 seconds for 100,000 elements. I'm expecting around 30 seconds for 1,000,000 elements. Now, for the purpose of this video, I'm going to speed time a little bit. So I'm going to snap. And in total, we produced 1,000,000 elements, and total time was 32 seconds on this machine. So we have a starting point from which we can optimize. Now, in order to improve any sort of performance on a system, we need to understand how it works. And in the form of a Kafka producer, the inner workings of a Kafka producer is neatly described by this little diagram that Giannis made. So when you send a message to Kafka, you call producer.send. So this is the starting point, and this is the asynchronous method that is being triggered by Java, Scala, or the Kotlin code that we have. And the message needs to be serialized first, and after that, a partitioner will allocate this message to a certain partition, and every partition will have pretty much an internal queue which contains multiple batches of messages. So the splitting of partitions rather is determined by the partitioner, and this partitioner allocates your message to a particular buffer. After that, some IO threads that are running all the time will pick up these batches from multiple partitions, and it will send to the Kafka broker. Now, in between these IO threads and the broker, there is an internal protocol with network buffers. So there is an internal ACK at the network level so that we ensure that these messages are sent to the broker. And the broker, once receiving the messages, it will persist these messages locally, and it will send all the messages for replication if we specify the replication, which we did in our cluster, and the replicas will follow back with an ACK. After that, the entire thing will send back an ACK, and hopefully, in the case of a success, this will notify back to the producer, and this whole process is asynchronous and non-blocking in the sense that we will receive a future. So we will follow that in the code, and if we get a failure or an absence of an ACK, we need to figure out if we need to retry sending the message, and there are a bunch of configurations here in this diagram, which you can also find in the blog post, and if we have the configuration set, this whole process will start over again if we fail to get an ACK. Okay, now speaking of the code, our crux of the method is produce, which also calls the very important send method in Kafka. Now, from Kafka's point of view, this is the native Kafka code written in Java, and the do-send method pretty much follows the same process. Some of the items in this process are invisible to us in the code, but I'm going to try to follow them here in the code. First of all, we need to serialize the record. This is one very important point. This is the first of the process. Then we need to allocate this item to a partition. So this line 1012 here in the code will allocate the item to a particular partition, and it will then allocate, or rather enqueue, this record to the proper batch, which is this accumulator thing, which acts like a buffer with, or rather like a queue with multiple batches. So when we say accumulator.append, this is when we store this thing in the batch. Now, after we store that in the batch, then we need to send the record to the broker, which is a bit opaque to us. So we have the sender wake up, and at the end we return the metadata of the record as a future. So this is what we obtain after calling send. Now we don't really care about using that particular result. We are simply going to use callbacks here when the send method has fully completed. Now, in order to improve any sort of performance in our producers, we need to trade off between latency and throughput. So this is where we might want to get back to our event producer and look at the configurations that we have here. So we have batch size, linger millisecond, and compression type. Now, if you send batch size and linger millisecond both configured to 0, so batch size plus linger ms to 0, that will do minimum latency. So you'll send the events as fast as possible, but lower throughput. Now, if you have a slow producer, you will want to decrease latency as much as possible because lower throughput is not your priority. However, if you increase batch size, so batch size larger, will increase throughput, but it will also use more memory, obviously, because you can allocate many items in RAM, but you eliminate the overhead of sending elements one by one. Therefore, sending them in batches is preferable in this case. Now, you might also increase throughput by increasing this MS config, because this configuration specifies how much time the client will wait if the buffer is not empty. So the records will be sent in a buffer if the buffer is empty, or at most this amount of time has passed. All right, so you can increase batch size and this linger millisecond to increase latency a little bit, but it will also increase throughput. Now, additionally, if you want to minimize the amount of data that goes to the network, you can also zip the data. So you can apply compression gzip. So if I uncomment these configurations and run my event producer once more, remember we took 32 seconds to produce 1 million elements. I can run this application one more time, and I'm going to speed things up a bit so that we can see how much time it took for these sort of configurations. So, snap. So at this point, we've processed 1 million elements again in time 12 seconds. So essentially, we've increased throughput 2.5 to 3 times as much. So these are some levers that you can pull if you are to increase or trade off between latency and throughput at the producer side. Now, switching to the consumer side, I'm going to show you a small diagram of how Kafka consumers work, again, courtesy of Yanis. Now, a Kafka consumer will maintain the TCP connection to the Kafka cluster itself, and in a poll loop will deserialize some messages, will fetch and process the records as our logic dictates, and it will optionally commit offsets. Now, by default, offsets are committed automatically at a regular interval. You can configure that, and you can trigger auto commit on and off. And there are a bunch of configurations that you can tune in this entire lifecycle. And on the right, we have the same consumer record, which we deserialize from Kafka. So here under the consumers package, I have multiple consumers that we're going to test. I'm going to start with a single thread consumer, which is the easiest one. And here we have also a configuration object here under properties. So we have Kafka config build consumer props. This is again a configuration object that was created here so that we don't have to type it all over again. So we have deserializers for every single bit. We have JSON serializers and deserializers as we write and read from Kafka. If you want to connect with a Kafka cluster with security props, with PKCS12 files, you can also do that. Okay. Now, this build consumer props has a bunch of parameters here that we can use in different situations. So we have e-commerce events group single. This is going to be the group ID for the events that we are going to consume. And we are also going to read from the earliest offset. And we also have this consumer resource, which was very similar to the producer resource earlier. The consumer resource was built to be generic here, and the consume is essentially, in a while true, runs a bunch of logic for us. And in run consumer loop, it will keep some internal state updated. And we are going to simply read a batch of consumer records. And for every one of these records, we're going to simulate a little bit of work, like 20 milliseconds waiting time. So we expect that the processing of every message takes at least 20 milliseconds. And we're going to do a bunch of logs. And if we're setting the per message commit, which we are going to deal with in a second, we're going to process some further logs. We're going to display them. We are going to update some internal state for this consumer resource. And we're going to log some lines so that we can investigate what's happening here. And we're going to deal with auto commit and per message commit a little bit later. Okay, now going back to this single thread consumer, this essentially processes elements one by one. Now, if we do the single thread consumer, we are going to see that processing messages from Kafka will take an obnoxious amount of time. For my tests for 10,000 messages from this topic, we are going to see around 4 minutes of processing time. So notice how the logs are going to show up. So we have resetting offset for partition whatever to fetch position offset 0. So for the earliest. Notice how much time it took for us to display the first log line. So 500 records from one partition. Records in batch, 500, and so on and so forth. Total group, and then we have another 10 seconds or so for another 500 records, and so on and so forth. So processing our 1 million pieces of data will take a lot of time. So obviously we can do better, and the level of parallelism that we can achieve in Kafka would be to scale either the number of consumers versus number of partitions, or the multi-threading aspect of every consumer individually. So the situations that we might find ourselves in are the following. First of all, if we have the number of partitions bigger than the number of consumers, all the consumers will share all the partitions and they will share ownership in between them. This is the scenario that we are in right now. We only have one consumer for all the partitions in the entire topic. The next situation is the number of partitions is equal to the number of consumers, which is the highest degree of per consumer parallelism versus the number of partitions, which means that every consumer is responsible for a particular partition. And if we have the number of consumers bigger than the number of partitions, we have the same level of parallelism, but the leftover consumers will be there in the case of fault tolerance. So if one of the consumers fails, the redundant ones will take the consumption from there. So going back to the code, we can increase the parallelism of this consumption aspect of our application by going to the per partition consumer, which essentially starts multiple consumers depending on how many partitions we have. So we are going to simply determine the number of partitions, and we are going to start a consumer resource for every little one through Kotlin coroutines. Now, if this is your first encounter with Kotlin coroutines, I have a long-form video here on Rock the JVM about Kotlin coroutines if you want to check that out. And you can also simulate that in Java or in Scala through some other mechanisms. For example, with virtual threads in JDK 19, or through an effects system in Scala, or equivalent mechanisms. So I'm going to simply launch on a new quote-unquote virtual thread, although the analogy here is not 100% accurate. So we're simply going to launch a new consumer resource, which is a new consumer for every partition. Now, if I run this application instead, we're going to see that the runtime is a little bit faster. So we're going to see groups being processed at the same time. So the time between the logs will probably be similar, but we're going to see a group processing 5 times the amount of messages that a single consumer would have. So the time between the log lines is the same, but we're going to process essentially 5 times as many messages. And that's not a hard limit on scalability because every consumer individually can be multi-threaded. So every consumer can have its own private thread pool with which you can consume multiple items from multiple partitions. And this is regardless of whether you have the same number of consumers for the same number of partitions. So we also have an example here in the code, which is parallel scaling consumer. So I also determined the number of partitions in advance that might not always be possible prior. So This might depend on your application, but I'm going to leverage that to, again, create another consumer for every partition. So we still have the number of consumers equals to the number of partitions, but here this consumer resource has this consumer parallel flag equal to true. And if this consumer parallel flag is equal to true, if we look at the constructor here, we say if consumer parallel, then the consumption is the consume parallel version, otherwise the regular single-threaded one. So the consume parallel version will create a parallel stream processor, and the parallel stream processor is implemented in an external library. And this is from Confluent. This is one of their external libraries called Parallel Consumer. You can find it on GitHub. I'm going to also link that in the description if you're interested in checking that out. This is essentially a wrapper over a regular Kafka consumer that leverages internal parallelism. And its main API is poll that will simply get a bunch of messages that you can process at the same time. And I'm doing another thread sleep 20 so that I simulate at least 20 milliseconds of work for every element in turn. So this leverages internal parallelism and it will fetch multiple messages at the same time. And of course, I'm going to do a bunch of logs and a bunch of state update for me. Now we can also run this one. So this parallel scaling consumer will be very, very fast because it leverages internal parallelism as well. So look at that. So we have records in batch 5 and so on and so forth. And I'm processing tens of thousands of messages per second. And because this is essentially killing my laptop, I'm going to cut that out very quickly. So I've processed 164,000 messages in just a few seconds, whereas the previous per partition consumer used to process roughly 2,500 messages every 5 or 10 seconds. Now, in our tests, we could process 10,000 messages with the single-threaded consumer in just about 4 minutes. And with this one, with the parallel processor, we can process 10,000 messages in a fraction of a second, maybe a few dozen milliseconds. So there's a 3 to 4 orders of magnitude performance difference at a consumption side, which is pretty crazy. All right. So that was a demonstration of performance optimization in Kafka, both for producers and especially for consumers. In the blog post, you'll also find some tips on offsets and how to handle them, but they were almost impossible to demonstrate here on camera in the video. So you will find those tips in the blog post as well. I'm going to link everything that we discussed in the video description, and I hope you liked it. If you did, go ahead and click the like button for me and subscribe to the Rock the JVM channel for more videos like this, and check me out on rockthejvm.com. I have hundreds of hours literally on everything in the Scala ecosystem predominantly, but we are going to also cover a bunch of other stuff, including Kafka and Kotlin and many more goodies like this. So until next time, folks, I'm Daniel, signing off.